Okay, so here's some vocabulary terms for radioactive dating. We've got radioactive elements, parent and daughter atoms, decay, so what happens to parent atoms over time, and isotopes. So let's actually take a look at some of these now. We'll start with what is relative dating. So our topic is absolute dating and half-life. The other way to tell how old something is relative dating. And for relative dating, all you can tell is something older or younger than something else. So if you've got rocks, usually rocks that are on top are younger and rocks that are on bottom are older. Kind of like if you had laundry and you threw laundry continuously in a basket, the oldest laundry will be on the bottom and the youngest laundry will be on top. So to find the age of the Earth, we would just dig down until we found the oldest rock on Earth. Well, no, that's not how it works with relative dating. Because here's the thing, Earth messes up rocks. It's called unconformities. Do more on it later. But you have things like erosion, washes away rocks, destroys minerals, water, wind, glaciers, and others. Places where you don't have deposition. So right now on land, rocks are being eroded away. They're not being deposited. Earthquakes, faults, plate movements, they can all change the rocks around, flip them over, move them into the ocean, dip them into the mantle. So rocks on Earth are destroyed. So relative dating doesn't work that well when you're trying to find really, really, really old rocks. It works great if you're trying to find if something's younger or older than a rock that's directly under it, though. So instead, we've got to use absolute dating. So absolute dating, you can see the definition right there, finding the exact age of an object. Now, one caveat while you're writing that down, when I say exact or definite age, it's not going to be like, if you're trying to find the age of something that's 10,000 years old, it's not going to tell you that that tree died on, Sunday, the 8th of June in 2008 or something. No, it's not going to tell you the exact day if you're trying to find something really, really, really old. But it will tell you its age, and it won't, not relative to something else. It will literally tell you it is this many years old, plus or minus this many years. Now, when we talk about parent and daughter atoms, let me just bring this up here. The original atom, when we say parent, that's the radioactive isotope. So when we say radioactive isotope, an isotope is just something that has more or less neutrons than, a different atom of the same type that has more or less neutrons. So for example, hydrogen, it could have one proton and no neutrons. It could have one neutron. It could have two neutrons. If it has two neutrons, it's radioactive. We would call that the parent atom. And then when it decays, we'd call that the daughter atom. So when we're talking about radioactive isotopes, they're just like regular atoms, just a different number of neutrons. And then once it's done decaying, it's called daughter. Now, here's the thing. Daughter atoms can also be radioactive as well. They could be stable, they could be radioactive. They have just decayed. That's all we know about the daughter atoms is that they have decayed away from being the parent atom. Now, when you're trying to date the age of rocks, the best rock is obviously igneous rocks. As you saw in the video earlier, igneous rocks, once they solidify, they trap in those radioactive atoms, and they're not going anywhere. They also trap in the decay atoms or the daughter atoms. They're not going anywhere as well. It also kind of works with metamorphic rocks because sometimes metamorphic rocks have melted and reformed, but it definitely will not work with sedimentary rocks. If you try to use absolute dating on a sedimentary rock, all you're going to figure out is when the minerals in that sedimentary rock were made, which is basically like dating an igneous rock. So works great with igneous, somewhat for metamorphic, not so much with sedimentary. Now, when we talk about half-life, the symbol for half-life is lambda. That symbol right there, lambda. Now, if you've played the game Half-Life or Half-Life 2, lambda is the symbol also right there. So good way to remember it, half-life, lambda. Lambda, half-life. Now, you may or may not see the word half-life on a question. It may just give you lambda equals 5,730 years, or lambda equals 4.6 billion years. So you need to know that lambda means half-life. What is half-life? Half-life is the time for half the radioactive nuclei in a given sample to undergo decay. Now, you could cross out the given sample part if you want. You could leave it. Whatever you write is up to you. But know that half-life, the time for half the radioactive nuclei to undergo decay. So if you have 10 atoms, the time it takes for 5 of those to undergo decay. If you have 100 atoms, the time it takes for 50 of those to undergo decay. If you have 1,000,000 atoms, the time it takes for 500,000 of those to decay. And when I say decay, we're talking a radioactive atom here. Now, for radioactive atoms, anything above 83 on the periodic table is automatically radioactive. 84 plus, all of those are radioactive. They have different levels of radioactivity, but they are radioactive. And even things that are lower on the periodic table, like carbon-14, tritium, even if it's under 83 on the periodic table, it can still be radioactive if it has a different number of neutrons, if it's an isotope. So keep that in mind. There are a lot of radioactive elements out there, and they're not just the big ones on the periodic table. The smaller ones can be as well. Okay. Now, when we talk about half-life, let's look at a little example right here. Let's say you start out with a sample. It's got 12 white radioactive dots. And then after one half-life, half of those white radioactive dots have decayed into green, stable daughter atoms. Well, after another half-life, of those 6 remaining, 3 have decayed and 3 are left. After another half-life, of those 3 radioactive atoms, 1.5 of those have decayed, and then the rest are stable daughter atoms. So you can see every half-life, the amount gets cut in half. So you start with 12, half of that is 6, half of 6 is 3, half of 3 is 1.5, half of that is 0.75. You get the idea. It cuts in half every half-life. Maybe you like percentages instead. So you start out with 100% of the radioactive atoms that you start out with. Okay. After one half-life, 50% is gone. Half of 100 is 50. After 2 half-lives, 25% remains. Half of 50 is 25%. After 3 half-lives, half of that 25%, 12.5% remains. And you get the idea, half of 12.5%, 6.25. So if you're doing percentages, an easy way to do it, take your percent, divide by 2, divide by 2, divide by 2, divide by 2. Just divide by 2 as many times as you need for how many half-lives there are. Maybe you're looking at mineral deposits. So you're a geologist. You're trying to date a rock sample. Well, this rock contains regular atoms, but it also contains radioactive parent atoms embedded inside the rocks or the minerals. And over time, the radioactive atoms decay into stable daughter atoms, and over more and more half-lives, those radioactive atoms will drop and drop and drop. You'll notice the biggest drop goes for the first half-life, though. The most red atoms became green in this first half-life, and then less and less and less of them decay because there is less of them. Let's do a chat questions to take a look at that for a... So every radioactive isotope has a different half-life time. And that's the key word when talking about half-life. Half-life is an amount of time. It could be days, it could be seconds, it could be trillions of years. And you can see this isn't even close to a comprehensive list of radioactive elements. There are so many radioactive elements, I wouldn't be able to fit them on this page with this font size. So you can get a range from trillions and trillions and trillions of years with indium-115, 441 trillion years. You can get down to half-lives that go into the seconds, the milliseconds, the femtoseconds. It's just, there's so tiny amounts that it wouldn't even, but there's no point in even putting them on here. So there's a lot of different radioactive elements, and they all have different amounts of time for half of them to decay. So if you had started, oxygen 22 at the start of whatever, a minute ago, basically none of it would be left. Because every 2.25 seconds, half the oxygen 22 goes away. If you had a sample of 100 indium-115 atoms at the beginning of the universe, it's possible that none of them would have decayed, or just 1 or 2. So you can see very, very big difference in the amount of time it takes for different atoms to decay. Now, some other key details about half-life. As you know, every element is different. That was the last slide. Nothing changes half-life. It does not matter what the temperature of the half-life is, or of the radioactive element is. It doesn't matter what the gravity of the half-life element is. It doesn't matter whether it's, sitting inside the sun, actually. It doesn't matter that either. It doesn't matter if you have 100 of them, 1,000 of them, 1,000,000 atoms. It doesn't matter if you have 10 million atoms. It does not matter. After one half-life, about half of those elements should have decayed. So if you add 100 atoms, 200 atoms, 300 atoms, you keep adding more atoms in there, you're still going to lose half of them after one half-life. Now, another thing to keep in mind, at least when talking about living things do not gain more radioactive elements once they die. So you gain radioactive carbon-14 when you breathe in and when you eat food. You are breathing in some carbon dioxide and you're eating some atoms that have carbon-14 bonded with them. And that gets incorporated into your body. When you die or when anything else dies, they don't gain any more carbon. That's it. They're stuck with what they have. That carbon is trapped inside their body. And when that carbon-14 decays into nitrogen, well, nitrogen usually isn't stuck inside your body the way carbon is. So that's how we actually can tell how old something is. So rocks don't die, but rocks, when they cool down from an igneous rock, their radioactive elements are trapped in the rocks. So living things, rocks, it's different, but they're not going to gain any more radioactive elements after they're made or die. Now, if you see a graph, with graphs, same thing. Parent isotope, the radioactive one, over time, the parent isotope will drop. It will not increase. And you can see every half-life, it drops by half. So it starts with 100%, drops to 50%, then 25, then 12.5, then 6.25, and lower and lower and lower and lower over time. So as more and more half-lives, the amount of radioactive isotope drops. Now the opposite, the amount of daughter atoms starts out with 0. If you look at, a dead tree, it shouldn't contain any unbonded nitrogen atoms just sitting there by themselves. So over time, the stable daughter atom will increase as more and more radioactive atoms decay, so that you end up with 100% of the daughter atoms where the radioactive atoms should have been. Now here's some radioactive elements, but that's not all of them. So let's say you're asked to find the number of half-lives. We're starting to get into calculations now. You need to know two things. You need to know how much time has passed and what is the half-life of the isotope if you're trying to find the number of half-lives. If you have those two things, you can use this formula right here. The number of half-lives is equal to the time divided by the half-life of the isotope. So for example, maybe 10 years have passed. If you have a half-life isotope that's only 5 years, 10 divided by 5 is 2. 2 half-lives have passed. So that's how you use that formula. Now, actually, this formula could also be rearranged. So if you know the number of half-lives and you know the time, you could find the half-life of the isotope. You would just need to move. If you want to use a shortened version of the formula instead of the written out word version, that's fine as well. Same thing, number of half-lives is equal to the time that has passed divided by the half-life of that particular element. So another example, let's do this one. So maybe you have a sample that's been sitting there for 10 days. So the time is 10 days, but the half-life of the sample is 20 days. So 10 divided by 20 is 0.5. 0.5 half-lives have passed. So you can get a decimal answer for half-life. That's fine. It does not have to be whole numbers. It can be decimals. So a half of a half-life in that example. So you can have less than 1 half-life, you can have more than 1 half-life, you can have exactly 1 half-life. It just depends. Use this formula to get it if you know these two things, how much time and what is the half-life of the isotope. Usually you can just look up the half-life of the isotope if it's not given to you, unless you're taking some sort of quiz in real life. Now, let's say you're trying to find the mass of a radioactive isotope. Well, what amount of mass is left over? You need to know two things if you're trying to find the mass of the isotope that's remaining. First of all, if you're trying to find out how much is left, you need to know how much you started out with, the original mass. You also need to know how many half-lives have passed. So to use this formula, you need to know two things. You need to know how much did you start out with and how many half-lives have passed. Now this works for decimal answers as well. You could have 2 to the power of 3.72. That's fine. Your calculator can do the exponent of 3.72. You could have 2 to the power of 0.5, so less than 1 half-life has passed. That works as well. So that is the formula you would use to figure out mass. Now, here's the thing. This is not the only formula out there to find mass. What if you didn't know the number of half-lives that have passed? How would you find the mass? Well, you could use this formula right here. So what if you don't know the number of half-lives, but you do know the years and the number of half-lives? Well, you can combine the first two formulas we looked at to get this formula. So mass, M, is equal to the original mass times 1/2 to the power of T divided by TH. Now, T divided by TH is literally just time divided by the number of half-life, or the half-life of the element. So let me back it up really fast. This exponent right here is literally this first formula we had right here. It's this, is this exponent. So this formula you see right here is just a combination of the first two formulas. Okay? So let's say you're doing this one, okay, you have 10 grams. So my mass is 10, or my original mass was 10 grams. I'm trying to figure out how much mass I have now. So original 10 grams, and let's say, I don't know, 5 years have passed with a half-life of 5 years. So 5 divided by 5 is 1 half-life. 1 half to the power of 1 is still 1 half. So 10 times 1 half is 5. 5 grams remain. Now here's the thing about putting this in your calculator. With that half right there, instead of putting 1 half in your calculator, just put 0.5. That's a great way to do it. So just put 0.5 to the power of instead of a half.